my God.
Yeah.
Okay. Can people hear me?
Yep. And now we have Philip Stump, who will move towards the more theoretical side of this discussion.
This is very strange. Okay. Good morning. I'd like to thank the organizers for this meeting, which looks very interesting. Let's see, how do I work this? This is where I spend much of my time. That's where UBC is. I want to talk about, actually I don't want to talk about this yet. I'd like to give some motivation for the theory here. I spent a lot of my career in condensed matter theory and also doing some experiments. And one of the things that's most familiar to us is the phenomenon of macroscopic quantum phenomena. I'll say somewhat more about that later to point out that they're not quite so macroscopic as you think, and that there are very severe problems associated with macroscopic quantum phenomena in general. We had a meeting in Vancouver 2 years ago where Jim Peebles was very strongly criticizing people working in inflation theory and pointing out that they were extrapolating quantum mechanics from the experimental realm of mass superpositions involving 34,000 atomic mass units to the universe, which was an extrapolation of over 80 orders of magnitude, and no such extrapolation has ever worked before in physics. So I'm going to emphasize that my opinion is that quantum mechanics has problems, and we should be looking for ways to, we should be remembering that and not just assuming that it's correct. So let me say a little bit about some of the problems with the orthodox way of dealing with the problem of unifying quantum mechanics and gravity, and say why I don't think that, personally I don't think that's going to work. That didn't work either. Hang on. Right. Okay. So the first problem is numbers. I'm not going to go through the numbers. You're probably very familiar with them. But the problem is that if we believe that the solution is to be found at Planck energies, then we're extremely far away from testing any theory. In fact, the energy density at the Planck energy is 45 orders of magnitude higher than experiments at the current LHC. And in fact, if one used a circular accelerator to test at the Planck scale, it would have a diameter of 5,000 light years. So the first problem is that a high energy theory is utterly beyond the reach of any conceivable Earth-based experiment. Second problem, and I won't spend too much time on this because I suspect that everybody's familiar with it, is that all of the forces apart from the gravitational can be understood using conventional quantum field theory methods, but gravity is not renormalizable. It's perturbatively non-renormalizable. Now, there are speculations that one can find an ultraviolet fixed point, the so-called asymptotically safe scenario. I hope this thing is asymptotically safe on my head as well. You know, oh God. Does that work? Okay, good. So, of course, people working in string theory or superstring theory believe that they have the Book of God in their hands and that they have a consistent theory, which they argue is the only consistent theory. It's certainly true that it's hard to build a consistent theoretical framework to unify general theory, relativity, and quantum mechanics. And the assertion by Hiroshi Oguri, who's actually giving a talk on this today at UBC, is that it's the only credible theory to achieve this unification. Many people would say that not only has it not achieved that unification, but that it's not the only credible theory, and that's what I will certainly argue. Now, this is a problem which has already been discussed, so I'll just very briefly go over it. The basic problem with low energy quantum gravity is that you have to consider superpositions of different space-time metrics. This has already been discussed in previous talks, so I won't say much more about it, except to point out that what it means is that, I can never figure out which button. Is this working at all? Oh yeah. That any event that in one metric is space-like separated can be time-like separated in another. And that's very serious if you try to put standard quantum field theory on a background space-time. It basically means that you've lost all notion of causality. Moreover, as was pointed out a long time ago by both Kibble and my colleague Bill Unruh, if you have wave function collapses, then you get non-physical changes in the metric, which in principle could even generate singularities. And it's hard to imagine that a measurement would cause a singularity to develop. So trying to superpose different space-times leads to meaningless results. Causal relations require a specific background space-time, and this problem has nothing to do with high energies. It happens instead when we try and write down mass superpositions, which is exactly the question being posed in this meeting. So, the argument that I will adopt is that we've been looking in the wrong place. We need a theory at low energies. But this has to be a serious theory. It can't be just some pastiche of Newtonian mechanics with non-relativistic quantum mechanics. We have to take the full relativistic form of quantum field theory, and in fact, we have to take the full general relativity. Otherwise, we're just avoiding the problem. We're trying to look away from Medusa's head. So let's see. Oh, sorry, and there's one other thing I wanted to say. This is my little rant about why I don't like quantum mechanics. I mean, I do like it. I've been using it almost all of my life. But the basic problem is that it throws that if you try, you can't take the wave function as a serious description of nature because it's different for different people. So people then say, well, it just describes the information that we have, but of course then you've lost the connection of the wave function or the state vector in Hilbert space with what is supposed to be physically there. Also, it devolves on this so-called measurement calculus, which is essentially brought in by hand from outside. Measurements are described in terms of projections and so forth, but they're extraneous and non-quantum. Here it is. So to divide the world into classical and quantum sectors has led to countless problems, as I think probably everybody is aware. In fact, the idea that quantum mechanics should be formulated entirely anthropocentrically, that is to say in terms of measurements made by humans, or as Bell put it, possibly humans having a PhD, but definitely not bacteria, is that it's completely anthropocentric and it's a throwback to medieval times. And I find it very difficult to accept. So this means that we shouldn't actually go in to a venture like this without being prepared to drop something in quantum mechanics. Also, something that's very important is that people have been pushing macroscopic quantum states ever higher in numbers of particles and so forth, and I'll say a little bit more about that in a minute. Okay. Yes, I'll say it right now. Here are some tests of superpositions in quantum mechanics that have already been done. First of all, you've already heard about these, the ones by Marcus Arndt, which I guess we'll hear more about. This is the molecule that was mentioned before. These are mass superpositions. There have also been phase superpositions, both in magnetic systems and in superconducting systems. But it's not generally appreciated that the level of so-called macroscopicity in these, or what Leggett called disentanglement, is much less than people realize. Birgitta Worley and her co-workers computed this for some of the experiments. And this is essentially telling you how many particles differ in the state by of order pi in phase. Well, of course, most of them differ in their state between the two branches of the superposition by far less than pi. So you can multiply the number of particles. You can take each particle, ask how much the phase has changed between the two branches of the superposition, add all of these up, more or less, and you get these numbers. They're not very big. Okay, so quantum mechanics is very far from being demonstrated at the macroscopic scale, and certainly not at the scale of the universe. So I'm going to say a little bit about this theory, which has got a lot of papers, and it's going to be a little bit hand-waving because I'm assuming that the audience here is not, or there's very few people in the audience are interested in the gory details of quantized gravity. So I'm going to give you a very hand-waving picture with the equations there if anybody wants to ask me about them. So in conventional quantum mechanics, one sums over paths. And if the object, so the blue is supposed to be some matter line, if the blue object interacts with some field, and they're both quantized, then we see the sum ends up looking like this. What you never see is an interaction between the paths. Why? Because it's a sum over paths. We're summing over individual contributions in a path integral. Okay? So this diagram is completely disallowed in conventional quantum mechanics. I don't have time to go over the argument, but there is an argument which is developed in these papers, which says that one can develop a version of the equivalence principle which says that if you compare amplitudes, if you compare collections of paths for single objects or for multiple objects, which are the same, then you'll find that they're essentially indistinguishable in the Einsteinian sense, and therefore we should be including this kind of sum as well, the sum over these interactions between the paths. So it was a very long job, basically by myself and Andrei Barvinsky, initially by myself, and then he joined me. He's a quantum cosmologist from Moscow, from the Lebedev Institute, to set up a formalism which was not only consistent, but which also we could use. So there are various forms that were written down, but some of them were more usable than others. What I'd like to do, just in 2 minutes for those who actually care about this sort of thing, is describe how it works in quantum field theory language. So gravity is a gauge theory, if you write it as a quantum field theory. The gauge transformations and the various analogs to Fadeev-Popov tricks, or what Jordan, who was a former student of mine, and I called boundary value Fadeev-Popov, is kind of messy for gravity. You have to introduce a gauge fixing field, here we are, here, and then you also have to introduce here we are, this Fadeev-Popov determinant, in order to do the same as what is done with ease in, say, quantum electrodynamics, and to derive a consistent form in conventional quantum gravity for the, here I'm talking about the generating functional. So the generating functional is well known in quantum field theory. It's the analog of the partition function in statistical mechanics. You take functional differentials of it to get physical quantities, and it can be written as an integration over a closed path, which I'm showing schematically here, which we chose, it's not the only possible choice, to be from minus infinity to plus infinity and back again, and then round the temperature cylinder. There are other ways you can do this, and the different ways you can do this are described in detail in the papers. What happens if you now introduce the possibility of gravitational interactions between the paths is you get a much more complicated generating functional, which is actually a product over individual ones involving more than one of these loops, in fact an arbitrarily large number of them, in which you have the interactions between the loops, okay? And there's a normalizing factor, this alpha sub n, for n loops, and you have to take the product over all of those. And it was a mess, and one of the most important contributions of Andrei Barvinsky was to say, look, why on earth are we working with this? It's like working with the partition function. Let's take the log. And that actually simplified a lot of the calculations thereafter. Anyway, after a long business, we were able to show that this theory had well-developed expansions in powers of h, the quantum of action, in powers of the Planck length, in other words, in powers of g, the Newton's constant, that if you let h go to 0, you had just ended up with standard general relativity. If you let g go to 0, you just ended up with standard quantum field theory on flat space-time. And that all of the Ward identities were satisfied, including all those to do with diffeomorphisms. So technically, it was interesting. And finally, more recently, we realized something very interesting. So actually, the person that got me to start publishing about this was Joe Polchinski, who I had a long conversation with about all of this in its very primitive form back in 2010. And to my astonishment at the end of this, he said, you should publish this. And I didn't understand why, and it was several years before I understood why. He had realized that this theory avoids the theorem that anything that's nonlinear has superluminal communication. In fact, this theory does not have superluminal communication. This is very interesting. I don't unfortunately have time to explain why that is. We'll be putting out a paper on it soon. But the consistency was very important. Many theories of quantum gravity end up with problems. They have ghost states, or they have unphysical sectors, et cetera, et cetera. And we really wanted to make sure that we did not have that. There's no point in having a theory which satisfies your philosophical yearnings, but which is mathematically inconsistent. Anyway, if you calculate with it, well, here's an example. Take the propagator of a matter system. So in conventional quantum field theory, you would integrate paths between two hypersurfaces and with interactions with, say, gravitons. I'm just doing, this is not perturbative, I'm just showing you typical graphs. I'm adopting the sort of 't Feldman view, which is that you can write a picture, and it doesn't mean that it's perturbative, it just means you're representing some quantity in field theory. So that's what I'm doing here. So this is conventional quantum gravity. This is the CWL theory, which, by the way, means correlated world line. The world lines are now correlated by gravity. So the propagator in conventional quantum gravity is between two induced metrics on these two hypersurfaces, and between two states of, say, a scalar field on the same hypersurfaces. And we've got to functionally integrate over all of those, including the relevant gauge factors. Same happens in CWL theory, except you're taking the product that I showed you on the last slide over all possible ring diagrams and then cutting them. Because the way you get a propagator from a ring diagram, in a set of 4 lectures I gave in Rio last week, I explained in detail how one does this. But you can basically take one of these rings and you just cut it on these hypersurfaces, and that generates a propagator. Now, a propagator in ordinary conventional theory would just be a line with maybe some hatched red coming off it, but in the CWL theory, you get something like this. And it's very interesting because a large number of graphs are 0. And the reason is that we have to take this product over an arbitrary number of interacting paths. And some of them are of different order in n, the number of paths, than others. And so, for example, at lowest order in perturbation theory, you're kind of shocked because you see that this diagram is 0, this diagram is 0, and this diagram is 0. These are all conventional quantum gravity graphs. But this one is not. This is an interaction between pairs of paths. And you think, how is that possible? Because we know that we can write down, both in the amplitude formalism for quantum gravity and also in classical GR when we do perturbation expansions, we can write down diagrams which apparently do contain these graphs. But the point is that the effect of the gravitation for a large mass, for a mass which is treated by standard GR, is to cause the paths to collapse onto each other. This is a phenomenon called path bunching. These two lines collapse, they're pulled towards each other, and then you end up with this graph. And in this case, you end up with this graph, and so on. And you can show that if the matter lines collapse to each other, you simply generate the standard graphs in a perturbative expansion in standard GR, which is kind of cute. Okay. I've been showing you lots of pictures, and they might make you think that this whole thing is perturbative, but actually we can get exact results in this theory. So if I actually ask what the propagator looks like, let me start off by writing a propagator for ordinary quantum field theory, for scalar field, in some fixed, frozen background space-time metric. Well, we can certainly write that down, and it can be written as e to the I times some phase factor, psi 0. In the full CWL theory, we have a different phase factor, capital psi. So what's the relationship between these? Well, the CWL can be written as this product. This is now with the logs. This was Andre's key insight, where each one of these k sub n's involves a very interesting object. It's the Einsteinian action, but for a space-time metric which is fixed on these two hypersurfaces. So the space-time metric can be varied, but only if you keep it fixed at the induced metric on these two hypersurfaces. And the matter phase is also dependent on that. Well, what is the equation for this Einstein action? Well, you take the functional differential of this action with g fixed in this way, and you find something very interesting. You find that the psi zero, the matter phase, is now what is sometimes called looks like what's sometimes called a weak measurement in quantum mechanics. That is to say, you fix initial and final states, and you ask what is the expectation value of some operator between them. And I would like to point out that this is in general a complex object, which means that the new Einstein equation is complex on the left and the right-hand side. That turns out to be rather important. So we can think of this chi mu nu, this object on the right-hand side, which would formerly have been T mu nu in ordinary GR, as an expectation value of T mu nu, but one which is conditional on the pre-selection and post-selection of the states of the matter field and of the space-time metric field consistent with that. So this is a self-consistent equation. And you can do the same analysis for the generating functional. Now, people have considered complex space-times before. There's a number of papers by Witten on them, for example, but for a quite different reason. Here they come out naturally. So I'm just going to very quickly summarize what we have so far. We've got a theory which is consistent in these various senses. It's also, it turns out, interestingly, a UV renormalizable. That's a whole other story. And it does not have superluminal propagation. And I've already described for you that you have these rather peculiar, very interesting formulas for the propagation of the matter field and for the analog of Einstein's equation. I'm going to show you now how to understand this intuitively by doing a thought experiment. Oh, actually, before I do that, let's just talk about second-order perturbation theory and see what it tells us. Well, the point is that the interaction between these paths causes them to orbit around each other. So when people say, give me a picture of, say, 100,000 paths orbiting around each other, I say, do the space-time diagram for a globular cluster. You've got all of these stars moving along, and they're orbiting around each other, and in fact, they're orbiting around their center of mass with fluctuations. Every so often, one of them gets kicked out because the three-body or the n-body problem allows that. But basically, it's more or less it's a conservative system. In fact, you need to couple the system to an environment to cause it to collapse. And in the same way, a globular cluster will last forever unless it moves through some gas field, in which case it will slowly collapse. That turns out to be crucial in discussing, say, the dynamics of the LIGO mirror in this theory. Well, I'm not sure if I have time to discuss this, but the interaction between the paths grows really rapidly as you increase the mass of the system. So the analog of the Coulomb radius for a hydrogen atom, the Newton radius, goes like 1 over the mass of the object cubed. The energy, the binding energy, analogous to the 13.6 electron volts for the hydrogen atom, actually grows like the 5th power of the mass of the object. And so, and this is what I mean, this is the binding energy, and this is the binding energy, and this is the analog of the Bohr radius. And so if you look at those in a picture, you see that for an electron, the binding energy is 10 to the minus 86 electron volts, so utterly unimportant. And the radius, the analog of the Bohr radius, is 10 to the 6 million Hubble radii. So you can see that an electron is not affected by this theory. And the question is, how high in mass do you have to go before you start to see things? And the answer is roughly 10 to the 14 atomic mass units. Depends on the kind of experiment. Okay, experiments. I'm going to talk about essentially one kind of experiment, which is, I'm going to talk about two path experiments, and then I'm going to talk about a real experiment, which is the result of collaboration between myself, Yanbei Chen, and Jordan Wilson-Giroux. So let's look at the two-slit experiment. In the two-slit experiment, we just sum over, we sum over contributions from this path and this path, and that, of course, produces the standard cosine interference pattern because it depends on the difference in the length between these two paths. Actually, we could also do it in conventional quantum gravity because we can't take gravity away, it's always there, so we should have included the gravitational contribution already in this calculation. But when we look at these phases, the phases along these two paths, that already includes self-interactions of the mass. Now, there are two theories we can compare this with. I mentioned, by the way, that it was Polchinski that pushed me into publishing this, but it was also a set of papers by Kibble back in '79, who tried to write down a theory in which the nonlinearity of gravity fed into quantum mechanics. And he came to a very interesting conclusion, which was that no such theory would work if you included the usual apparatus of measurements in Hilbert space. So he tried to write down quantum mechanics without Hilbert space. And I found that interesting, which was one of the reasons that I did this in a path form. Well, we find that both semi-classical gravity and the CWL theory give different answers from ordinary quantum mechanics. But they also give different answers from each other. I'm not going to go through these formulas, which are very nice, because they make predictions for what interference pattern you would see, and it would be different from standard quantum mechanics. I'm just going to try and give you a feeling for it. So let's do this theory in the weak field regime, where the gravitational fields are small deviations from flat space-time. Then essentially what happens is that the standard two-slit interference result requires an extra phase, this theta 2-1. And for weak fields, that has a form that was written down in the last lecture, except that in the last lecture we had T00 here and here, whereas this is this chi00, which, remember, is a complex quantity. It's the expectation value of T00 between 2 points in space-time here, and of course that is in general complex. So what we have then, I tried to describe this in words. We separate out the global phase from this, the interference part. The gravitational term is the path integral for the classical action integrated along the classical path in the configuration for a metric field which is sourced by both of the matter paths, okay? And the matter term sums over the two matter paths in the presence of the same background metric. So the matter is still propagating quantum mechanically, but it's propagating in a different field, partly because the paths are interacting with each other. So let's compare, see why it is that semi-classical theory gives a different result from the CWL result. Ask yourself the following simple question. If I have a particle moving along two different paths, so that the wave function at any time t is a delta function of it being in one position or the other, what does T00 look like? Well, the answer is it's the sum of the two contributions. On the other hand, in semi-classical theory, it's a delta function of the average of the two. This is a point that was made very firmly by Kibble way back in the 60s. Different. And so we get a different answer. I'm not going to discuss this experiment, which I think was first discussed by Baumeister et al., but you actually get, again, different answers in this experiment for CWL theory than what you would get in standard quantum mechanics. But the real problem here is we need to understand how mirrors work in these theories. Mirrors are complicated objects. So these are the people. We produced a very long paper in Phys Rev D earlier this year, and there's more coming. Let me just give you an idea of what, and I just learned that Yanbei was prevented from coming here by some problem with flights. So there's a very simple description of cavities, which I am assuming that everybody here is familiar with. Basically, the mirror is pushed by the photon field, and we end up with a system which is basically a pair of coupled harmonic oscillators. one is being the cavity photon field and the other is the mirror, and they exchange energy back and forth with each other. And you can define a function here, which is the integral with time over the coupling function here, which is in the interaction representation. And basically that, if that is equal to n times pi, then you've returned to your initial state. In other words, if you start off with all the energy in the mirror, it's now back in the mirror. But if it's n plus a half times pi, then the energy has been entirely transferred from the mirror to the photon field. Okay? So it's pretty simple. Problem is that we need to know the interaction of a mirror with itself through gravitation. In other words, if I imagine the mirror proceeding along two different paths in space-time, the two branches of the superposition, what is the gravitational interaction between those? Well, of course, all the mass is in the nuclei. And it turns out that for an amorphous system, the effective interaction between the two looks like this. The width of this spike here in position space is roughly 200 to 300 Fermi. It depends on the phonon spectrum of the system. You can calculate it at zero temperature and at finite temperature very, very accurately, because we know what the phonon spectrum is for these systems. If the system is crystalline, it's different, and I'm not going to go into that. And this, inside this potential, is how the paths are orbiting around each other. What is the frequency of that orbiting time? Well, if it's high temperature, if it's LIGO, the depth of this spike for the LIGO mirror is actually 24 Kelvin only. Okay, it turns out. So at LIGO, we're up here, and the period is 21 minutes. So you're not going to see any difference from standard quantum mechanics, no matter how hard you work. But it's 16 seconds inside this spike. And in fact, this is, if we cooled LIGO to low temperatures, this behavior would change. Well, there we go. Well, we were actually able to solve this problem exactly inside the spike. And we found a rather disappointing result, which is that if we treat the spike, if we imagine the system is sitting at the bottom of the spike in a harmonic well, then basically the difference with standard quantum mechanics is zero. Sorry, where did that go? Yeah, we can prove that the problem simply becomes a problem of n plus 1 oscillators coupled to each other bilinearly, and the predictions of quantum mechanics are identical to those of CWL theory. So the real challenge then is to go to a nonlinear theory, which we started to do by the following ruse. We said, supposing we do pulsed optomechanics instead of just looking at LIGO doing its thing. So we now apply, we have the laser field taking this form in time. And the purpose of these square, actually I never know what you're supposed to call them in English. Anyway, the purpose of these is to actually deliberately engineer the transfer from, say, the mirror to the laser field in such a way that you're basically driving the system back and forth between the two oscillators. And the point is that it turns out that this allows you to find out what the ground state of the system looks like if you're at low temperatures, and it's not the same as in ordinary quantum mechanics. And the reason is that the attractive interactions between the paths cause what would normally be a Gaussian ground state to be squeezed inwards. This was already known from Schrödinger-Newton theory. I should mention that Schrödinger-Newton theory turns out to be what you get from CWL theory if you go to lowest order, that is first order in perturbation, and then do a mean field approximation. Then you get Schrödinger-Newton. But of course, if you sum to all orders in gravitation, you'll get something different. Here was the problem. When we calculated this, we found that the difference between the two ground states, which would be quantified by asking how many excited phonons were there in the mirror ground state, if you tried to overlap it with the ordinary Gaussian state, we found it was given by the ratio of the Schrödinger-Newton frequency, which is the frequency of oscillation inside the spike. So remember, that's basically a time scale of 16 seconds, to the mirror frequency itself, which in LIGO is typically, 50 hertz, say, Well, that's a ratio of maybe 10 to the 3, 10 to the 4 to the 4th power. So the deviations from quantum mechanics are of order 10 to the minus 15. Not helpful. Of course, what it means is that if we were able to change the frequency of oscillation of the mirror so that it was very close to that of the oscillation in the spike, then we would see very large deviations from quantum mechanics. But the other way to do this is just to do nonlinear experiments. I was going to talk a lot about dissipation and decoherence, but I suspect I'm running out of time. Nope, nothing is written. Sorry. I just see a pretty picture. Oh, I've got 7 minutes. Well, it turns out that one can also incorporate the effects of environmental dissipation into the CWL theory. Of course, there's nothing gravitational about them, but you can do that. It's rather messy. There are two kinds of environment that are important. One is phonons, but the other, as was mentioned in the last talk, thank you. The other, as it was mentioned in the last talk, is coming from junk. So the mirrors, if you describe them as a solid-state physicist, the mirrors are nothing but an assembly of two-level systems interacting both through dielectric and through strain forces. That is a very well-known problem in solid-state physics. In fact, it was called by Phil Anderson the most important problem in condensed matter physics some time ago. It's hard because the forces are long range, which means that you get all sorts of funny collective excitations, and it means that the dynamics is not so easy to predict. It also means that if you look at the dependence with temperature of the dissipation in these mirrors caused by these defects, it's very strange. There are very well-known phenomena associated with this, the so-called universal dissipation at low temperatures and the big dip around room temperature, and these have never really properly been explained. And they are described in the theory by what's called a spin bath environment, which is an environment of two-level systems. But you also have the phonons, and the phonons, of course, interact with these two-level systems. So it's a mess. And with Rana Adhikari, I've been spending a lot of time trying to do something that would be useful to understand how to better design these mirrors. We're also working with some material science groups in Stanford and Berkeley. I don't think I have time to talk about this, so I'll just move on. Well, here's a key point, that if the Q factor is very, very high, then you might ask, how long does it take for these paths to collapse onto each other? And the answer is a long time. In fact, it's given by Q over that oscillation frequency of the paths around each other, which if you put Q at 10 to the 10, is 5,000 years. But of course, you never, I mean, the mirror is never left in a high Q state. When you're preparing it and so forth, it may be in a very low Q state. So there are a number of interesting experiments that suggest themselves about how to prepare or not prepare the system with the path collapsed. If they're already collapsed, they're not going to orbit around each other. There are all sorts of other interesting designs that we have, but I think I've run out of time almost, so I will finish with a quote. So I've emphasized that consistency, internal consistency in the theory is really crucial. And we spent maybe 5 years trying to make sure that it was internally consistent. And this was myself, Andrei Barvinsky, Dan Carney, who was mentioned before, joined us on one paper, and Jordan Wilson-Giroux. But there's another consistency that's also important, and I dare say some of you have seen this quote, which you can actually watch him delivering online in a YouTube video. And he says, he's talking about theory in general. He says, if it disagrees with experiment, here we are. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your theory is. It doesn't matter make a difference how smart you are or who made the guess or what his name is, her name is. So it could be the Queen of Egypt, or it could be Einstein. If it disagrees with experiment, it's wrong. That's all there is to it. So we need the tests. And this is what people like myself, Jan Bay, Jordan, Dan, and others have been working on, making definite predictions. So thanks for your time.
We have time for a few questions.
And those are the references if you want.
Robert.
Yes.
Yeah.
A fellow Canadian.
Yeah, hi, thank you. So, I've got two questions I'll ask. Maybe you've gotten these a lot. So my understanding is that the idea is that the superposed paths effectively gravitationally interact with each other, and you're putting that in. So my two questions are these. One is, I see all the pictures. I know you've worked on it, but it looks to me like a clever person could rewrite the entire thing as a new kind of path integral. Is that right, or is that actually not possible?
No, it's not correct. So actually, sorry, what's the name of the guy in Florida who did a lot of Keldysh stuff in quantum?
Clauser?
No, after him.
Sorry, I can't remember.
Yeah, sorry. He actually made that point when he saw the original form of the theory, which was in this summed version. The problem with the summed version is it completely disguises the fact that you're really dealing with a product of analogous to the partition function. And so you might say, oh, well, I certainly do rewrite that in the same way. But, you know, I think I can convince you pretty quickly that that's not the case by asking you to take the partition function of, say, a strongly correlated gas of bosons and rewrite it in the terms of a set of independent bosons. Not true. I mean, one of them is just an independent gas of bosons, and the other is, say, superfluid helium-4. The spectrum is different. Everything is different, okay? And all the correlators are different. So I would answer you by saying no. Okay. And
Okay,
your other
well,
question?
I could pursue that. The other one is, you say, I mean, I got a lot of questions, but I'll take only two. So the other question is, you get, if I understand it right, instead of the semi-classical Einstein equations, you get a complexified thing. What is the meaning of the real and imaginary parts in those equations?
Yeah. So we only have two answers to that question so far. I do not think that we have a general understanding of it yet. We understand how it works for weak field theory, and in that case, basically it just shifts fringes and makes the amplitude larger than it would be in some areas and smaller than it would be in others. So it's basically killing the fringes in some areas and not in others. I'm not sure if that's the question you're asking. It's
not. It's what is the meaning? Like, is the metric complex? And if
yes.
So there's like a lot more degrees. There's like twice the number of degrees of freedom in the metric now because it's complex.
Yep.
So I'm just trying to understand what, like, you're saying what might happen as a result. I'm just trying to ask, like, conceptually, what is the meaning of it?
So when I was talking about this with Roger Penrose, he said, well, these are my nonlinear gravitons. I'm not sure if that's true. But I would say we don't really understand yet. But you're absolutely right. You have doubled the number of degrees of freedom in that respect. But you said, sorry, you had another question. Well, that is the other question. Okay, yeah.
We have a question from Zoom, actually.
Hello. Hi. A very, very interesting talk. So I just wanted to know, so to get a difference from the Newton-Schrodinger equation, what kind of experiments do you have to do? Like, to what precision do you have to go to get the difference from this lowest order Newton-Schrodinger?
Right. So let me just repeat what I said before. And the proof of this is actually in our 2022 paper, which is one of the papers up there. That the Schrodinger-Newton equation comes out of this theory if I stay at lowest order in perturbation theory. That is, I expand. I mean, of course, you can make an expansion in powers of g and take it to infinite order, or in terms of the Planck length. If I go to lowest order, and then I do a mean field approximation. So it's the analog of doing a Hartree approximation for those who are familiar with that. So obviously, if G is very small, then there won't be much difference between Schrodinger and Newton in this theory, but of course there won't be much to see either, because you're looking at a very weak correction to quantum mechanics. So where the corrections to quantum mechanics are not negligible, the difference with Schrodinger and Newton is large. Does that answer your question? One would have to discuss specific experiments in order to answer it in more detail. Sorry, who am I talking to?
Sorry, hello, I'm Sogato. Hi, I'm just joining online. Sorry.
Okay.
Thank you for the talk. So at some point you showed this product of things that look similar, partition functions.
Yeah. But for an interacting system.
But then at some point you wrote that the entire theory satisfies Ward identities and is renormalizable.
Yeah.
Could you, and it involved metric and meta fields. Could you be more specific about what is the gravitational dynamics and the meta fields that you are including in this game?
I'm not entirely sure what your question is. Are you asking about the renormalizability, or are you just asking about the dynamics?
I'm asking because, I mean, is it renormalizable for any kind of meta fields that you put?
Oh, that's a good question. Okay, we worked it out for a scalar field for particles, but I suppose you're asking, well, supposing I took...
You put a standard model, for instance.
Yeah, exactly. Well, that's a little bit of a complicated thing to do. I think there are more important things to do before that. To be honest, we didn't care that it was renormalizable. The person who said, oh, I'm sure your theory is renormalizable, was Jim Hartle. And the reason he knew that was because he'd actually once worked on a model in which he had n scalar fields, independent replica fields, and noticed that it was renormalizable in the large n limit. And so he just basically guessed that this would be renormalizable as well, and he was right. But we don't really care, because this is a low energy theory. You know, I mean, hydrodynamics is non-renormalizable. Nobody cares. Right?
Yeah. I was just wondering because of your statement. So
yeah.
Okay, thank you very much. So now we go for lunch. It's